Okay, shall we start? So yeah, let's start the second talk of the session. It's my great pleasure to meet Professor Fino from FIU and the University of Fino. So yeah, she'll talk about canonical metrics in complex geometry.
First of all, I want to thank you very much for the invitation to give a seminar, I thought, in this nice conference. It's a mixture of different topics. So my talk will be especially on special types of Hermitian metrics. Some of them we already saw, like pluriclosed metric, but we'll see also some type of metric, which are called balance metric, will be in some sense transversal to the pluriclosed metric. So let's start from motivation. I use this term canonical metric. That doesn't mean for the moment anything. So let's start. Okay, let's start. Let's take a manifold, a minor manifold. So it's natural to ask if you can have some canonical metric, usually imposes some condition on the character. One very nice theorem, and also very simple, is the uniformization theorem that says that any complex Riemann surface has a metric of custom Gauss. And especially there, you use the equivalence between complex structure and conformal structure. So that is the theorem in complex dimension 1, right? So one can ask what happens in other complex dimensions. In Kähler geometry, the problem can be, we already saw in other talk, can be to find metrics with special chemistry property like Kähler-Einstein, complex characters, we said this morning in unit talk. In non-Kähler complex geometry, you can speak about many types of Hermitian metrics. I will focus in two types: the balance metric, balance that was called by Fino as semi-Kähler, right? Metric, or a pluriclosed. So let's start one motivation for balance. So the first part, I will focus on the balance case, and then I will go to the pluriclosed case. So the last part is more related to generalized geometry, let's say. But the motivation for studying balance metric comes to also to Calabi problem that was formulated in two talks previously. And before to that, I just reviewed some notation. Okay, Kähler in some sense, this is extending the diagram because you can think that some complex manifolds are more complex than the other. Okay. Okay, we say that the Riemann, so J will be always a complex structure, so a complex structure, and we say that the metric is the J Hermitian compatible with J, it is also yeah, you have the orthogonality condition in point, and then you can construct in a natural way the two forms, which is the fundamental form, the Kähler form, and often I will use, instead of using metric, I will use only as a metric. So if you fix the complex structure, then it's the same thing. You work on the metric, on the form. And we know that in Kähler, if you have not only the complex geometry, but also the symplectic. So omega is the symplectic form. Exactly. And we will work on weaker condition on that. It's one thing that is in the Kähler case is already different, but we will see in the non-Kähler case is even more different. Is the complex dimension is 1, and I get complex dimension, and the complex surface is special. Okay, in complex dimension 1, everything is easy because the two forms automatically closed, so you always yeah. But and other natural examples are complex torus, complex projective space, and the locus of homogeneous non smooth projective the complex projective space. What happens in complex dimension 2, bigger than 2? Then we have some topological condition, some restriction in the complex, like the object number to be given, the fundamental group is the special time, and then we have the formality, the central rational, the central part. And this is not only distinguish the Kähler case by non-Kähler, because you can have manifold, complex manifold, which are formal, or Latin manifold, which are formal, but they do not understand. Okay, the common surface is very special in this case. This was chief announced by Calabi-Yau and then proved by Fino, the classification of complex surfaces, and then using currents by Dahl, independently in the morning, and it proves that the complex surface is Kähler. It's only the first Betti number. So only with the first Betti number you can distinguish that, and this is not anymore true in either dimension. And let's go now to the motivation. So the first thing I want to do yesterday, we saw already also today two formulations of problem in a different way. Let's see this way that is more related to the expression to the Ricci form. So let's start with Kähler manifold. Locally, you have your polymorphic coordinate, complex coordinate. So you can write omega in that description, right? G alpha beta bar, just the components of the energy. So a thing that you have here, this is not anymore systematic, it's not here. The Ricci tensor is the Ricci connection is automatically J, right? And you can write this is just a local expression of the Ricci form. You can see that you know that it is the 1 1 form, right? And we justify that the second derivative is the log of the derivative geometry. And even if it is a local, this form defines a global defined form, psi 1 1, which is closed. And that's represents the Torsion class. So the conjecture posed by Calabi was okay, let's take 1 1 form, which is closed, and represent the Torsion class. Can we find a Kähler form such that the Ricci is exactly that form? And the conjecture was solved by Yau. I don't want to, this was already mentioned, right? That if we start with a Kähler, and then we take a cross 1 1 form, such that the form is representing the first class, then there is a unique form with different subs, such as the here we got to that. Okay, complex dimension 1, this is just you can do like natural uniformization theorem. And if P1 is 0, that's a very interesting case because you can get Ricci. And that's essentially one example of how mathematics for which the Ricci is contained second, meaning the growth, if then it's a complex. So there was many types, we say, of attempt to generalize the Kähler in non-Kähler setting. Okay, the first thing that one can do is this is the applying the different case in non-Kähler case. Just take a complex manifold, and we will say that this is Kähler or not, it doesn't matter if it is it's Calabi-Yau. If the canonical bundles are multiplicated. So that means if the complex dimension is 10, then there is another variation of the form, which is the so the question is, okay, let's take this type of manifold. That's the way we are into the complex, actually, which canonical geometry you want to choose. What type of method you can choose is what is called a conformity balance. So by conformal change, you get a balance metric. And that's come essentially from the first, not the first, but one of the generalization of Calabi-Yau that is related to Hull-Strominger. Let's see that. Okay. I will review a little bit about balance metric, and then I will see a new construction balance. I will review a little bit what I get in the case of Hull-Strominger system, but also recent construction that we get with Geograntera and Misha related to the construction of extension and letting go. And then we'll go back to the list as a form. We'll see another construction. Okay, let's start. Balance. balance or semi-Kähler. The name balance is due to Michelson, and essentially it's just a metric which fundamental form is equal. So you have n minus 1, n minus 1 form, which is equal in this case. Was shown by Bismut that the condition is can be viewed in terms of the Laplacian. Here involve three Laplacian. The Hodge Laplacian with respect to T and the Laplacian with respect to del and the more. But then essentially found its characterization in terms of balance that you cannot have because it's current for degree 1, which are components of the balance. This is essentially the other structure that you know for a cup. For a cup of complex manifold on meter not the balance match, because using that you can show that the manifold, the copper manifold, can meet any complex manifold or combination complex manifold combination in one homologous to zero. And for instance, this gives an answer for the Calabi-Yau manifold that was mentioned in one of the. Here you just take the construction that makes the reaction over the product of the two complexes for the one. So in this case, you cannot have balance, but you don't know if you change the complex. So you don't know if I mean or not. Balance. Okay. Other example. This was in Gale thought the twistor space of a four-dimensional oriented anti-dual Riemannian manifold. That is the balance metric. But there is another way that's nice. This essentially the balance condition is filtered by modification and then by linear. So you can get your compact, let's say, balance manifold, just starting with a Calabi-Yau and apply a bimeromorphism. And monoton manifold are made if you start with these are the bimeromorphism to the Calabi manifold. And the more general Fujiki class is just bimeromorphism to Calabi manifold. But there are easy examples, like if you start with a unimodular complex group, so the complex actually is binary. And you just take a compact quotient by then you get the compact example. For instance, you got down if you want one of that. There is also construction. This is a little bit, let's say this construction is a little bit dual. What's happening for the copper-real group, or any copper-real group of even dimension as pluriclosed matching, right? Here we have no compact, simply group of linear flat that's related to the composition of symmetric space. And always you have in one, you're limited on the structure, always you have the balance. So you can see already a separation, right, between the balance and the other condition, compact and non-compact. Okay. I will explain a little bit how we already saw some suspension in this organization when we were mentioning near manifold whatever that can be described as a manifold suspension. So okay, you take a different and then you just take the product of your manifold and the closed interval, and then you just the we will actually on one. And then if you take the projection on the second system, then you have another projection on S1 and the fiber is up. Okay, so you have a small fiber bundle with base S1, circle, and fiber M, and the structure group of that is just the second group generated by the differomorphism. Okay, one can define in another way the quotient, just the product M times R by the deduction. So given by that, you apply the power of your differomorphism and the translation. But yeah, and then you have the differomorphism. Then you have always a natural closing on part. Just you take the putback, the length of part. And then this is the theorem due to Tischler, and proof is that when you have a common manifold, you can identify when it's a methodological expression, if you don't use it, it has a non-dimension. And mean manifold and common function of important groups of probability are examples of special type. This example. I just mentioned a little bit what is known for solvmanifold case. We consider this remark, in fact, reviewed with Gale using another result by the book. Essentially, we use this every time you have something like G over gamma, like before, and then which is manifold in general, a little portion by relative, you could use the minimum result that you have been one variable before, and then you just do something which is not invariant, and you get something more. So essentially, you can look about here. Of course, everything is working because we are using the J is invariant. So it's coming from some power structure at the level of the algebra, and there are some classification results for the important case. In fact, it's quite a tricky definition for violence. It goes more into cases. That's a little strange, but that's a thing. And also, I consider another case that is related to the complex Calabi-Yau that I mentioned before, because it's a case that you have a solvable, the algebra, or modular, and you have an holomorphic view. So, at the level of holomorphic, if you look at the aspects of manifold, you have a holomorphic trigger. And then there are other results that I get with my student Paradiso in the almost abelian case and almost important cases. Anyway, I just want to mention this construction that is nice because it's related to the twist construction. The twist construction by one can be used also in terms of one. Like to the post and maybe the midnight. And in this case, can be applied. This is a generalization they call private one, they call the share conjecture. And if related to the fact that you don't use the action of the group like the other case, but you use two factor boundaries, essentially with some property about the torsion. So, but the nice thing for this construction share that is preserving the balance condition. And you can get any two-step solvable algebra applying the share constructor to the abelian one. So the switch, right? The one that you get for T1 and the case that you know this right? Okay. Let's go to. I will present a part of the design, not all the design, but the one we consider this type of what we call hyperbolic suspension. Okay, the motivation comes from this paper, this structure by Fino and one, where they construct these six-dimensional manifolds, which are on the same type of the Calabi-Yau. We already saw it, but also for these lessons. One to take on the one of common structure, one to take the question part, associated with the common structure and not the different. So you can also talk about these are so they only describe it, but they didn't describe any result about any existence of a special match. So the other question is okay, they cannot meet the bar. We see that. Of course, we put a question because the answer is yes. But on the other hand, we should. I will not mention the two in that case, but we show that they will not meet any pluriclosed. So any omega positive form such that it is not omega. So that's using correct. I will describe the construction, and then we see how we draw. No, not. So this will be a special homogeneous construction. Okay, let's start with a very simple surface, the Kummer surface. This is the most compact surface that you see blowing up the 16 double point that you have here, right? Which is and you just portion by the evolution. You use by the multiplication by -1. And then, okay, you can describe in another way. You can also describe as a function of f where f is got the same data, right? T2 is equal in any singular point, and just like in evolution, you do it by that. Then the fixed point set is the union, right? Or the sectional divisor or the singular point. And if you take the just 1, 2, or the 2, you just say this is a 1, the 2, which is the 2, 0, 4. This is use the number dimension 2, 0, 4, because if for that, you use the other one 2, 0 on the that's the standard. Now we need the different. That is not our different. That's come from the construction. So let's take a matrix with coefficient with the plus and the 1. And then you have this condition on the modulo, which way you can choose and diagonalize the word. And let's call it lambda and lambda minus of course the inverse because it's this one, the inverse. And let's take that okay, or the inverse math that you have in the cohomology, the first cohomology. And this is that's 4, and also sectional point right? So it's a finite or a morphic explanation, preserving the U or the far. Good. So let's take this as okay, in the second factor, you can see that it's doing now, right? Just doing selection on R, to stay there, and then on 2 just this by A. And this is used in a natural way in action on the product of what? Times R times. And the question is exactly the compact. The compact complete manifold is really a canonical method that will be exactly in the field. Yeah. Oh, yeah. No, I denounced before already that complex orbits, right? I already denounced before like that. So let's say we have the figure is a special type of define. So you just take it. Okay, you start with a complement, and you take a automorphic, which is the complement. Just automorphic, not the matrix. You can and we call this the proposal in terms of the cohomology, the action of that on the real continuity, and it's a unit of the vector and the heavy value with 1. Using such automorphic of the complicator and the lattice, by T1 and T2, then you can construct this hyperbolic torsion extension. This is, let's say, this is secondly. In fact, you can do the same taking 2 holomorphic automorphic we could use with more general. This is a special case related to the previous construction. In this case, okay, you have a method, the product of the method size 1 because it's doing nothing, right? In the second part. Okay. We apply this. I mentioned this result, but it's more general, and I will explain why it's more general. The example, the one that we mentioned before, is in particular not on Kähler, but it's a it's a compact hyperkähler. So if you start with compact hyperkähler, and you take a hyperbolic automorphism, we preserve the holomorphism. Okay, when you use it, here that preserving the holomorphism preserve the volume, right? So you can generalize that considering more general something preserving the volume. The 2 holomorphic automorphism are preserving the volume. Essentially, we prove that that type of suspension has always a balance matrix, and the previous construction is just apply this case to the case. How we prove that? don't want to say. In fact, we use essentially the projection. Right? If you look at projection, this is the projection essentially of a computer, and the only thing that we check is that this is the result by. We just check the depthness is what we can call attention. So we need to check that the pullback of the volume on S1 minus 1 as the non-trivial essentially bot check. So it can be plus 1. Okay, one can do the same thing essentially using the same method, applying the real portfolio. The same thing, exactly the same thing. Same type of instruction. And here you get something which is a manifold in this case, but almost familiar. And of course, if you are working on that, the method is easy. Right? So another question here is, okay, can we write the method? Because the result is in terms of so we didn't have an expression. So we know that it is not valid, but we don't know what it is. So this is something that we don't know.
Excuse me.
Yes, I'll go back.
In your construction,
Yes.
what kind of manifolds will arise from this? For example, if I consider general Kähler manifold,
You mean a topological?
What kind of?
Okay, the complex structure is described to the name of the. Yeah. Never clear. Yeah. We do that they are very. Yeah. But the topology in general, we don't have, I mean, we know that they are for intersection.
They have like strong questions.
Yeah, they have some. Yeah.
Some of the basic.
Yeah. Yes.
How would you know how do you use it? It's hyperbolic.
In fact, it's more general. In fact, it's more general because we use just the preserve the volume. This is we don't use hyperbolic. I use I state the theorem to the hyperbolic because to explain that the previous structure is
I mean, the point is, the output doesn't is okay. Right?
Yeah, the important thing that doesn't.
Otherwise, the metric will be easy. Yeah.
And then it's here.
Very sure that.
Yeah, it doesn't. So, but yeah, that's very good. But in principle, you can use also two if you want.
Yeah.
Yeah. Yeah.
You start with the real part of, but you use some structure for reading book or not? Just
We start with this. That's why we standard. We standard. No, we in principle. Okay, you need to start with something which is clear, right? So if you think about the book again, you only try to solve.
okay.
But in principle, what is that you use?
Oh, this is good choice.
But of course, you can. Yeah.
Just asking you think, but it's people think that they.
Yes, that is possible. In fact, the section, I think if I am wrong, but the nearer point about the section, you only need the fiber is one.
Yes,
but it's not that you out yeah, the rest of the structure.
And it's, I'm afraid it was restricted to dimension.
Yeah, exactly.
Not sure.
Yeah, yeah. But for Kennedy, what is not saying, yeah.
And how much geometry depends on this of this curve?
Yeah, I mean, you mean to change the automorphism,
Yeah.
then you change.
Yeah.
Yeah, because the topology model can be described in terms of the action of the This is, I think, was done, I don't know if it's but it's Monday, and yesterday, you said something that how it's working, how starting the album, the people read the commodity. So the commodity
Then I can speak kind of entropy.
and
In
let's see what you mean.
basically, you would have used on the space this temper fundamental vector field to the top.
Yeah.
And the flow is, I mean, on each fiber. If you assume this kind of flow, on each fiber, the flow like intersects in terms of seconds. In a certain way, yes.
Okay. Yeah. I don't know what you mean by that. No.
Any kind of way.
Okay.
Question about entropy.
Okay. Okay. But this type of structure will not admit anything close. Yeah. So it's S balanced, but not pretty close. Okay. Here I just reviewed something because it's more related to what I was saying before. This is a relation with physics. I don't want to talk much about that. I just mentioned the construction. And this Hull-Strominger system that we will see in a moment was described independently by Hull-Strominger. And it gives a compactification of a chaotic supersymmetry between, let's say, time dimension and 4 dimension in constant state. So locally you have an axis and then 3rd dimension, which is locally applied in the constant space in the compact manifold and the gauge to bundle. The compact manifold has been set and reviewed as a system. One of the talks. And the idea is to reduce the equation required by superstring theory to geometry of the 6 manifold and factor the count. Okay, the link with Calabi-Yau problem comes from the result by Candela, Hull-Strominger System. And that is the case when the flux free, the flux is essentially the torsion related to omega and then it's just 1/2 r d of omega minus 1. So essentially when it zero the 6 manifold Kähler, and to find so that the final solution is just to find some Kähler machine. And that is exactly what we want, the motion for the Calabi structure. In non-Kähler case, that was exactly how when you have non-zero flow, same flow. And then in this case, so the difference between the two cases is essentially the matches that you have in the flow. In the first case, you have a problem. Here we have 1. And in this case, the compact 6 manifold is here Calabi-Yau is in the sense of compact state, okay, holomorphically canonical bundle, holomorphic tree. And the question are essentially we start with compact manifold combination 3 with holomorphic. And we denote by omega the non-vanishing form. And then we have a complex vector bundle and an Hermitian metric along the fiber. And alpha prime is a constant. Okay, from physical point of view, alpha prime has to be bigger than 0, but not necessarily makes sense. Also, alpha prime negative. The Hull-Strominger system. Okay, the first equation is just a Hermitian equation. Here, FH is the temperature of the chain connection. Let me think of the normal form with value in the morphical. and that is the stability. But I don't want to say about that, but essentially the stability in that case. Called the polymorphic factor bundle. And then here that is that the second condition is the condition appear the condition that if you change the metric, if you do a conformity, you get the balance condition. And then the third condition is what comes from the canonical choice of the metric, because this involves the curvature, right, of the chain reaction on the bundle, on the homomorphic bundle, but also the curvature of a connection that is is a unitary connection in the tangent bundle span, and the full Yau solution choosing number equal to the chain. Sorry, but physically point of view is not the right choice of connection. Okay. This I think I already set up why you get the Ricci flat. In fact, you have not only you have a choice of unitary connection because by Duchamp we know that you have a one understanding of Hermitian. One is a champion, and the other one that has more physical is a Bismut. I will go back to this. Was already mentioned by Gale and characterized by the condition that the torsion essentially combined with the argument. Now I will present the conjecture very quickly that we get for the choice of the chain connection. But before that, I just mentioned some of the results and not all the results. But the first construction is always showing Yau, and it's using essentially tonicization of the surface, and it used the construction by Goldstein, and that is the generalization is wrong. I know because sorry, but look. Okay. That's the generalized Calabi-Yau. Okay, and then the construction only the root and common. I think Fernandez, Ivanov, and Guarte Villacampa, and also yes, consider what especially right the phi was the product, I think, of the 5-dimensional realizable over the course over lattice minus 1, but that is example. And that's maybe, yeah, I want to consider the complex group of the question with all possible connection. And then this is related to the duality, but it is not, maybe I'm wrong, is a duality adapted to the solution of the Hull-Strominger balance. And this was done by Baraglia, and after the figure is an adaptive action. But he constructed in Maria construct solution to that, and these are the first examples he was. That's one. And then there are other results by one, and then other, but I will not mention. Let's go to the construction by Goldstein and Prushkin. I will review a little bit. I will explain how we essentially will generalize. Considering of the case surface a case in R before, so special type of singularity singularity. So let's start with case surface with a Ricci flat Kähler matrix. Then this is the standard construction by Goldstein and Prushkin associated to, so you just take a pair of fancies dual one such that represent the integer homology class. And then you can construct in a natural way the thorough operation, and essentially you define the construction such that the reaction is morphic, and you have a natural. So I really note by theta 1, the 2, the connection 1, 1, and then you have this vertical form or 1, 0. theta equal to P, theta 1 plus I theta 2. Okay. The answer for the bottom, to get a bottom symmetric is quite natural. You just take the pullback, okay, the Kähler metric, and then you just find I theta theta bar, and this is bar in a natural way. And for Yau, just modify that using the scalar function. And you see that the vertical part will be the same. You just do the pullback of the exponential of that. That's what you get. And this is the common conjecture equation that you get to get the solution and the positivity condition for the matching. And here you have some data like non-function and the choose to form new with integral of the integral, essentially with average 0. Okay, what essentially we use okay, let's take the good metric of such people. You have enough information. So you can think that like a forgetting manifold, right? And working on that, so working that essentially the argument by putting out is working also on this type of relation, which is transversal to Calabi-Yau. We are studying what we are. This is just a corollary what we proved, but essentially what we proved, we found that maybe the second case is more interesting because we found new connected example of complex manifold with trivial canonical bundle, which are a solution to the Hull-Strominger system. Here the full Yau on top. I will say one thing how we got that. And I am saying also that our pre-students in fact are working a little bit because in the paper we choose one case we are before, that was the inspection of two hypotheses of degree 6 in a special type and the way projected space. And the type of singularity was very simple because we had isolated singularity type in 1 and the classification, but in principle one can consider also other. Okay, we follow that looking and see they can fill up. You see, here we have a connected sum starting from 14 up to 22. That's the time when we choose the second number. How you go up. The question is, okay, can you have more? I don't want to put that. We go now to the but to construct that, essentially we used a construction unicular that was favored one bundle. This was used in the powerful construction for any manifold. Here we are, so we first applied, we first construct the center as one bundle, and which is more, and we are conditioned to assure that. And using by the whatever, and then we can tell a regular as one bundle. But I don't want to mention that. I want just to mention that it's possible with this vibration. Look at the games are called vibration. So again, these called vibration are quite special. Okay, let's go to the Bismut connection. Okay, in general, let's start with Hermitian manifold. We know that there is a unique Hermitian connection for which the torsion is a free form. This is more general, but anyway, in the case of Hermitian, essentially the torsion, you can see from there that it just with the omega, where we see that operator. And the pluriclosed corresponds to the environment, but on the same time corresponds to closed function for the Bismut connection. For proper dimension 2, you can see that that notion is in fact the good shot, the condition to be good shot. So here you can see the proper dimension 2 for pluriclosed for balance case is given here. And here, by the good shot result, this is a common surface, and you are in the conformance, you just do a conformance, you can find a new method which is pluriclosed. So to enter the close, for covered surface is not, is giving nothing. But in other dimension, the situation is completely different. How much time I have? So, because I feel
15 minutes.
okay, very good. So now we know of complement parameter. This even dimension complement group, we can meet also generalized here. Okay? So, in this case, the visual connection is there. So from this point of view, and it's not known, there are no single example of complement which has the visual connection, which is vertical. Okay, in manifold, we have now a structure here about that. Total space of holomorphic, total quantity in that. For complex and manifold, there are results. You can tell the that is entirely active, and then there is optimal result, and private is one. But there is also construction, and this is related again to the construction of total value, right? Of the scalar, this is due to Grancher, Leo, and Paul. They proved that for any positive integer, greater than equal to 1, then that connected sum is a pluriclosed. Okay. Then this was generalized later by Podard and Pascal. And they proved that the total space of principal bundle of a projective manifold with one of that structure group, unitary, spatial orthogonal, or compact symplectic, is in fact is also pluriclosed. So it's true that there are some constructions compact manifold admitted pluriclosed. Okay, this is a conjecture that we put in the study, and we talked about it. Balance and pluriclosed are transversal in the sense that if you import, okay, you fix the compact structure and you import the matrix to be on the same time balance and pluriclosed, then this is clear. But what happens if you fix the compact structure and you ask, okay, two different, one balance and one pluriclosed? So the moment every example of this is balance, in fact, it cannot be pluriclosed, including the construction that I mentioned before. Twisted space will by addition and so that case. But in the non-compact, in fact, there are conditions. These are due by private one, and they construct at the level of the other. So in that case, so the compact case is special for that point of view. And now I finish with the generalized Kähler. I will present something of the standard theory on this project. Okay, we saw it. Part of it, I just review very quickly the notation. Okay, we know that generalized complex is just complex. Okay, on the tangent, on the direct side, on the tangent bundle, cotangent bundle, which is integral with respect to the ground. Generalized Kähler, this is the definition given by Hitchin and Pascal. We saw in many tools now, so it's a pair of generalized complex structure which commute and are compatible with the natural pairing, right? Between tangent bundle and cotangent. And also have the second condition, let's say, the positivity. Okay, and we have this characterization. This is the name pluriclosed, because that's proved by Guattari. And essentially, in terms of Hermitian geometry, what you have a matrix G, which is compatible with two complex structure, And such that you remember this was the torsion, right? The torsion of the Bismut connection. So you have to essentially the torsion of station of course group, because that's the pluriclosed case. We already saw that when the two complex structures are meeting or not commuting, is given different parts of the manifold. When they are commuting, I could split. I don't know if it's just because you are splitting at the tangent bundle and the two eigenphrases relative to 1 minus 1, then natural evolution, which you have. I'm not splitting them. Okay. A total angle change is classified how the total sectors which are made to be by a Newton solved, and one of them is the node surface of type. Okay, this type will now focus on your type, and then we can describe it as solved the manifold, and the type is essentially the two level. And what's pointed out by Abdullah, that this innovative is in fact a couple of and we know by itching that if you have a non-split generalized structure on the upper end, then the commutator together with the inverse complement you define all multiplication. Okay, what we know so because on covenant dimension 2, the covenant we know the material question is happening. Okay, for the Newman case now, because it was okay, we know that by counting one square, 6-dimensional manifold having variant, structure, this is not anymore true if you go to complex movie. There are generalized complex structure, and for generalized Kähler, you cannot make any variable. The non-example of generalized Kähler or manifold until now are all almost zero, and they were all free. That's what we know, and then in a paper with Adriano Tomassini previously, we construct some example, and also with my student Paradiso. So, and all the example was so we had in two with my students that there are examples which are generalized Kähler. They need to be in a real dimension A, and they are not related. So the one and here I just report the structure equation of our, let's say, associated algebra. But one thing that this is something that we are working on here in fact some results okay. In fact, in this example, the component is a suspension of the system. On this level, is not given. Now we are working, this is a working project in my student, to look more general. And in fact, we are so we construct essentially, which is correct, very good quality. We start with the Kähler times solve or the algorithm. So, and doing some algorithm, we cover this, but it's new. So this is the more general thing, but we don't cover any general Kähler things like that. So they are non-Kähler, which is true. We can prove that in many cases. This is something else. So this is not how with general Kähler is like for I hope that we soon for the fact we already And I think I finished here, so I hope that I am on time. And thank you very much.